Well, ladies and gentlemen, I stand here as the ghost of Christmas past, about to hand over the baton to my successor. I'd like to begin, and I'm absolutely not going to make a speech, so don't be nervous, by saying what a great honour and a great pleasure it's been to have been your president for the last year. I have done my best to put on a fairly full programme, although we were stymied a bit in January and we had to close down again for COVID. But other than that, we've had a reasonable programme, and I think for a lot of meetings a reasonable turnout. It was a great sadness to me that we couldn't have our dinner because, frankly, no one wanted to go to it, or very few people did, and it would never have paid its way. And I think, and I'll say this to our new president, the low point was when the chief executive of the Nuffield Trust came to give us an extremely good talk to an audience of 5 people, 2 of whom were myself and my non-medical wife. But these things happen. A lot of our meetings were quite well attended, and for that I'm very grateful. I would like to thank our core staff here of Mal, Anna and Sharon, who've held the place very much together. I really would like to say a huge thank you to our new chief executive, Sean, who has been, he's at the back there, hello Sean, a tower of strength, and has really changed enormously the way that we've been able to run the institution. And I should also thank the Strategic Management Council for endeavouring to keep the show on the road. It's now my great pleasure to hand over the presidency to Professor John Wilding, who will be known to many of you. John Wilding leads clinical research into obesity, diabetes, and endocrinology at the University of Liverpool. He was a graduate of Southampton University in 1985, where he continued his clinical training until he moved to the Hammersmith, where he undertook specialist training in diabetes and endocrinology, followed by 3 years of laboratory-based research into the neurobiology of obesity and diabetes. He came to Liverpool as a clinical academic in 1996 and was appointed Professor of Medicine in 2005, and he leads specialist services in severe obesity at the University Hospital Aintree, which was designated a centre for obesity management by both the UK and European associations for the study of obesity. John's research team focuses on developing new treatments and strategies to reduce the burden of obesity and obesity-related diseases. He's published over 350 papers, chapters, and review articles, which made my 20 seem rather insignificant, really. Which include obesity clinical trials in obesity and diabetes, adipocyte biology, functional neuroimaging of appetite in obesity and endocrine disease, and studies of metabolism in obesity and diabetes. He chairs the NIHR National Clinical Research Network Metabolic and Endocrine Specialty Group, and he's a member of the Royal College of Physicians Advisory Group on Nutrition, Weight and Health. He's a past chair of the UK Association for the Study of Obesity and president of the World Obesity Foundation. It gives me great pleasure to hand over my medal to John Wilding, and the very best of luck for the future. Turn around now.
Yeah.
Try and fasten it for me. There you go.
Either that or you're going to strangle me.
I'm a surgeon. I'm good at this sort of thing. Not. There you go. Thank you very much.
Thank you very much. have that. And I think we also have a little token for you from the Liverpool Medical Institution. There you go.
Oh, thank you very much. That's lovely. A little badge with the institution hissing Sid the snake on it. Thank you very much.
Thank you. Well, thanks very much, Jim. And it's really great to be here. And I can remember when I first came to Liverpool, and I think it was probably Gareth Williams that introduced me to the Liverpool Medical Institution when I first came here, which is now 26 years ago. And I was just impressed by this wonderful building and the atmosphere and the opportunities for engaging in academic discourse and medical discourse at this place. And I think I've been to a lot of meetings here. And in fact, for a long time, we ran the UK obesity course here, probably for about 10, 15 years, between about, I would say, 2000 and 2015. So it has a lot of fond memories, and it's fantastic to be here as your president for the next year. So what I'm going to do in the next, hopefully 45 minutes or so is talk a little bit about work that I've been involved in, but I want to try and put it into a bit of historical context. And I'm going to focus mostly on diabetes. And I'm going to talk a bit about type 1 diabetes, which isn't my main area of research, but is something that is obviously a very important part of diabetes care, as well as type 2 diabetes. I will touch on obesity as well. And I'll also touch on some of the people and the things that have sort of happened to me during my career that I hope will at least try and keep you interested in between the boring bits where you're seeing data and so on. So just a couple of points before I move into let's make sure I get this right. Let's use the arrows. Just a few disclosures. I think it's only fair to disclose that I do work quite closely with industry, pharmaceutical industry, as part of my work. I think it's right to make these associations open. The pharmaceutical industry is very important at supporting medical work. And as I've said, most of the funding we get is either research funding or is most of that goes through the University of Liverpool. What I'm going to talk about is the history of diabetes, really, and we're going to look at the past, present, and future, and hopefully there'll be something in this for everyone. So we'll start with the past, and I suppose I got interested in diabetes actually when I was a medical student. I actually did a fourth-year project with a physician in Liverpool called Brian Leatherdale, who was a fantastic physician. David Ewins is in the audience here, will remember him well. And he really inspired me to be interested in diabetes. I also spent a student elective, and I managed to find some photos of that in Sri Lanka in 1983, which was not a great time to go to Sri Lanka because the civil war started the day after I arrived in Colombo. But nevertheless, I got quite a lot of experience there in diabetes management in a developing country. And as you can see there with my long-suffering wife, Helen, we also had the chance to visit some of the amazing architectural and archaeological sites in Sri Lanka during our time there. You can see I'm quite a lot younger and I look a bit like a hippie, but there we go. That was student life in the 1980s. I also think, before I move into the main part of my talk, I want to acknowledge the fact that Liverpool actually has a great history of diabetes, and I'm grateful to Ian McFarlane for loaning me these slides. Ian was a colleague of mine at Aintree who retired a few years ago. Because in fact, it was in Liverpool that the first observation was made that diabetes was a state of hyperglycemia. In other words, that the raised glucose wasn't in the urine, but it was in the blood. And this observation was made by Matthew Dobson, who was a physician working in Liverpool in the 18th century. And in this journal that probably most of us haven't heard of, and certainly doesn't have a very high citation index factor, Medical Observations and Inquiries, he produced this article, and the key points in this are just in the next couple of slides. So this gentleman was admitted to the hospital. He had quite a long stay of several weeks for investigation of his diabetes. I don't think we'd be allowed that length of stay these days, but they managed to take 8 ounces of blood from him, and you can see that it had a buffy texture. The serum was opaque and it resembled cheese whey, so he's describing their diabetic hyperlipemia. And it was sweet, but not as sweet as the urine, and I'll leave you to your imaginations as to how he determined that. And then this gentleman had quite significant polyuria, and you can see that there was a white cake which tasted sweet that came from the urine, and the same cake, as they describe it, was found in the blood when they dried it down. And again, he concluded that these both were sweet and they were both sugar, and that they and that this meant that the sugar was raised in the blood and that the urine was secreting sugar because it was raised in the blood. And that kind of summarizes, that's the summary, if you like. He's saying that the saccharine matter was not formed in the secretory organ but previously existed in the serum of the blood. So that was the first observation of hyperglycemia in diabetes made here in Liverpool. So that's a fantastic observation. So I said I was going to talk about 100 years, and I think most people kind of celebrated the discovery of insulin last year in 2021 because that was when insulin was first purified by Banting, Best, Collip and MacLeod in Toronto. But in fact, the first patient wasn't treated until 1922. So this is 100 years since the first patient was treated. And you can see that Leonard Thompson, a 14-year-old lad dying from type 1 diabetes, was the first person to receive injection of insulin. The first time it didn't work that well. He was still ketotic, but then they purified it further, and he had a second injection a little bit later, and it was possible to normalize this young man's blood glucose without obvious side effects. A lot of people associate these photographs with Leonard Thompson. In fact, this isn't Leonard Thompson. We don't actually know who this photograph is. It's a young man called J.L., but we don't know. We know the initials. We don't know the name. But this is the one that's often associated with Leonard Thompson, but actually it wasn't him. And you can see this young man was treated a lot later, but does demonstrate the power of insulin and this amazing discovery that completely made a previously inevitably fatal disease into one that was treatable. So is that it? Problem solved? Of course, the answer we now know is no, because it's very difficult actually to mimic the normal secretion of insulin in the body with injections subcutaneously. It's not as simple as replacing something like thyroid hormone, which is a tablet, of course. And what emerged over the next decades was the observations that people with diabetes, although they didn't die of acute hyperglycemia quite so much and ketoacidosis, that they developed complications. They developed high rates of cardiovascular disease, and they also developed specific microvascular complications, particularly affecting the eyes, the kidneys, and the nerves, leading to amputations, blindness, and end-stage renal failure. And in fact, of course, we now know that there are a lot more complications of diabetes than that, some of which are listed here. And of course, the social implications of being diagnosed with diabetes are significant. And we're still, I've looked after, nowadays you can see people who are airline pilots with diabetes. That was not allowed until very recently. Heavy goods drivers with diabetes was not allowed until very recently. And part of the developments that have occurred in diabetes care have been what have allowed those things to happen. But nevertheless, there's still a lot of prejudice and stigma associated with having diabetes. And now, the other point that I think it's really important to make is until 2 really landmark trials were done while I was a junior doctor that really changed the history of diabetes, and I had no involvement in these trials other than working at the Hammersmith alongside Eva Kona, who was an investigator for the diabetes eye side of the UK PDS trial in type 2 diabetes. But until these trials were completed, the DCCT trial was the Diabetes Control and Complications Trial in type 1 diabetes, conducted in the United States and published in 1990, that looked at good control against poor control, and the UK PDS, which asked the same question in type 2 diabetes, which was not published until 1998, in fact, after I came to Liverpool. We really didn't know whether it was possible to control diabetes well enough to prevent these long-term complications occurring. But what we do now know, and this is the DCCT and the long-term follow-up after the trial was over data. These are quite old slides, as you can see. But you can see the design here was that you had a group of people who were treated conventionally with once or twice a day insulin, not much glucose monitoring, not much care given, and another group who were given intensive insulin therapy that included some of the early versions of insulin pumps, or 4 times a day, multiple daily doses of insulin with frequent glucose monitoring. And they achieved quite a big difference in glucose control. You can see here 9% in the conventional group in HbA1c in old money, 7%, which is close but not normal, glycemia in the intensive group. And the green line demonstrates the incidence of microvascular complications of diabetes in the control group, and the yellow line here, the microvascular complications in the intensive treatment group. Dramatic difference. And the interesting thing was that persisted even after the end of the trial, when the two groups actually converged in terms of their HbA1c, but those differences actually persisted. So if you've got that good period of early control for a number of years, it actually had a long-lasting effect on those patients' complications. And that was also true for cardiovascular disease, although that didn't emerge until 17 years of follow-up. You need to do really long trials to get the answers. The UK PDS asked the same question using the drugs that were available at the time, which was insulin, sulfonylureas, and metformin in type 2 diabetes. And without showing you all the detail here, you can see that there was a benefit of all of the therapies for microvascular disease, and although the numbers were very small, an apparent benefit for metformin also for macrovascular disease that included heart attacks and strokes and mortality. And if we look at a bit more detail about the cardiovascular protection with metformin, that seemed to be maintained again after the end of the trial. We have this legacy effect where the good control during the 10 years of the trial was translated into further benefits even longer in the 20-year follow-up. So 10 years after the cessation of the study treatments, when everybody kind of tended to converge again, we still see reductions in things like heart attacks and strokes, and you can see that here with the, again, very long-term follow-up and that very persistent effect to reduce complications. Of course, the tools that we had in those days were quite limited. We really only had, for type 1 diabetes, insulin, which in those days was given largely by needles and syringes. Patients didn't really have much opportunity to monitor their own glucose until the 1980s, when the first glucose monitors arrived. They were testing their urine, which is pretty crude. And we really only had 2 classes of drugs. We had sulfonylureas that were available everywhere, and metformin, in fact, wasn't really made available in the USA until after the UK PDS was published. And I highlighted this before. The challenge of type 1 diabetes is, if you look at what insulin does in a healthy person during the day, you can see that it's up and down a lot. The grey bars here are the concentrations of insulin through the day as you eat meals and so on. So it's going up and down to keep your glucose pretty much around 4 or 5 millimoles per litre most of the time. And to try and mimic that is really difficult, and you can do it with what we call a basal bolus insulin regime, where you give long-acting insulin to last through the day and then a bolus of insulin with meals. But that's quite an inexact science. It's really difficult for patients to be able to do that, to work out the right amount of insulin to give with a particular meal. It depends not just on the carbohydrate content of the meal, which is what most of our dose adjustments are based on, but also on what else is in the meal, because that will alter the rate of absorption of the carbohydrate. So it is quite a complex thing, very difficult to do. And one of the problems that we saw, for example, in the diabetes control and complications trial, was although the patients did better in terms of the complications, they had a lot more hypoglycemia, which is not very pleasant if anybody's experienced it. And they also gained a lot more weight, which is a side effect of giving insulin subcutaneously as opposed to through the portal vein where it's supposed to be delivered. So it's really quite difficult to do that. And during this sort of historical period now, we did have the development moving on from insulin syringes and needles with a bit of inaccurate dosing to more accurate dosing with insulin pens. I couldn't actually find a picture online of the NovaPen 1, which was the one that came out when I was a house officer in Liverpool, in Southampton in the early mid-1980s. This is a more modern version, but I did manage to find the old BM sticks, and people still talk about BM monitoring. BM actually stands for Boehringer Mannheim, which was the company that made the sticks, and that is an old-fashioned BM stick. It took a big drop of blood, and it took 2 minutes to get an answer, and then you had to judge it against the colour. And you can imagine that somebody with diabetes who's got visual impairment, it's pretty difficult comparing the colours on those things. So it was never particularly easy. People had ideas around that time that maybe it was possible to measure the glucose in a more active way and then infuse insulin continuously. So the first insulin pumps, and in fact, although it was a research tool, this will make you laugh, the Biostator was developed in 1977. This was the first attempt at a closed loop system for type 1 diabetes. As you can see, it's not particularly portable. And I think it became, it was used as a tool for research to understand, what happens if you give insulin slowly and measuring blood glucose and so on. It was never really seriously thought about as a treatment. But it does show that people were, even in the 1970s and 1980s, were thinking about the idea that you could perhaps automate this, measure the glucose, and somehow adjust the insulin in response to what was happening to the blood glucose. But clearly, we didn't have the technology in the 1970s to do that very effectively. So, as I've said, I spent my junior doctor years and my training mostly in Southampton. I had a little foray into Dorchester to do surgery, which was exciting. I'm looking at Jim there. And then I went back to Southampton, did my membership there, and then I was really very lucky in that, with Brian Leatherdale's support and support from other mentors in Southampton, particularly Steve Holgate, who respiratory physicians here will probably know very well, who looked after me when I was working on the respiratory ward in Southampton, encouraged me to think about an academic career, and I applied to a range of registrar jobs, but the first interview I went to was for the Hammersmith, and I ended up meeting this chap here, Steve Bloom, now Professor Sir Steve Bloom, FRS, who is a very well-respected, highly cited researcher. I mean, you were congratulating me on my 350 papers. Steve Bloom has over 2,000 papers. So I don't think I'll ever catch up with him. I think he's unique. But I spent some time at Ealing Hospital, funnily enough, as a gastroenterology registrar, because that was the way things worked in those days, and learned to do endoscopies and things, which I was never very good at. But what I really wanted to do was get into research, and Steve encouraged me to do that. And I applied while I was doing the registrar job for an MRC fellowship, and then started working on in the laboratory, which I'll touch upon in a minute. But that kind of got me interested. Because I was working on the neurobiology of obesity and weight control, it got me interested in type 2 diabetes and why obesity and type 2 diabetes might be linked together. So that kind of now, we're starting to move a little bit more towards the present now, but before we get there, just a couple of points, because I've talked about type 1 diabetes. I want to talk a little bit about type 2 diabetes. these observations come from the United States, from the Nurses' Health Study, and they show this very strong relationship between body mass index as a measure of obesity. It's not the best measure of obesity, but it's the one that is used. And you can see that as your weight increases, your risk of diabetes increases exponentially. And we know that type 2 diabetes is partly related to insulin resistance and partly related to a decline in beta cell function. So insulin resistance probably comes first, and the beta cell function goes down with that. So you actually have to have a double hit to get type 2 diabetes. So the obesity drives the insulin resistance, and what we now think is probably the case is that it probably also partly drives the beta cell function dysfunction on the background of genetic differences in the ability to secrete insulin, the ability to increase insulin response to insulin resistance. I'm not going to go into the science of that in great detail because we'd be here all night. The other part of the work that I got interested in was this very strong association between obesity and diabetes and cardiovascular disease. And what we knew then, and we know a little bit more now, is that as you gain weight, particularly if you gain weight in the central region, it seems to be associated with the development of insulin resistance. It's associated with the development of hypoglycemia, dyslipidemia, hypertension, a systemic inflammatory state, and a hypercoagulability state. And all of that is because of substances that are secreted from the adipose tissue called adipokines that include factors like PI1 and interleukins and so on that drive the inflammation. And that probably contributes to atherosclerosis, and it also means that once you've filled your subcutaneous fat stores, you have to put the fat somewhere else. And where it ends up often is in the liver, in the muscle, and also even in the islets of Langerhans, in the beta cells and around the beta cells of the pancreas. And that's probably what drives the development of the decline in insulin function and leads to type 2 diabetes and also, illustrated in this slide, non-alcoholic fatty liver disease, which we know is very strongly associated with diabetes and also a significant cause of morbidity and mortality. The other piece of work that is a little bit more recent that kind of fits into this story quite well is the observation by Roy Taylor and colleagues in this very small but very neat experiment, and I actually examined the PhD for this work, where they took 11 people with relatively recently onset of type 2 diabetes. They were moderately obese, BMI of around 33, and what they did was they put them on a 600 calorie a day diet for 8 weeks. So really very limited amount of food, 2 milkshakes a day basically. And you can see what happened. Their glucose pretty much normalized. That's a normal glucose value there of around 5, and you can see it went from 9 to 6 within a few days of going on this diet, and then it was maintained throughout the 8 weeks. That's hepatic glucose production, so the liver stops producing excess glucose, the liver fat falls, and we also know that the pancreas fat falls. They measured that by magnetic resonance imaging. And that was the idea that you could reverse diabetes through weight loss. We kind of knew that before, but this mechanistic study really made that very clear. And that means that people have known this for a while. We've associated obesity with diabetes. So what happens if you try and get people to lose weight? And this study is the Look Ahead study, which was a big clinical trial done in the United States that looked at people with diabetes and tried to get them to lose weight and maintain that weight loss. In fact, it was a long-term study that went on for 10 years, but this shows the first 4 years. And you can see that people lost weight, but then they gradually regained about half of it over 4 years. And in fact, if they carried on, when it carried on, they actually regained most of that weight. It's really difficult to maintain weight loss with dietary means alone. And the HbA1c fell, but then also tended to go back to where it was before. So it's really hard to do this through lifestyle measures, and this is just one example. I could show you lots of other examples. On the background of that, and in fact, really before this study was published, but in the context of that knowledge, I was quite interested, as I've said, in appetite regulations, because we kind of realized that if you were going to be able to treat people's obesity as a way of treating the diabetes, you actually had to understand why some people eat more than others and what the differences were. And we kind of knew quite a bit around the time when I was doing my PhD, which was around 1990. We knew that there were some signals in the brain that made you hungry, because most of these studies were done in rodents, but you know that if we injected a peptide called neuropeptide Y, NPY, into rodents, it made them really hungry very quickly. And some of the other neurotransmitters here also made you hungry, including some of the opioids. And then we also knew that there were some signals from the gut that decreased food intake. Cholecystokinin, which is the hormone that makes the gallbladder contract, also seems to have a role in satiety. We knew that glucose in itself and insulin reduced food intake under some experimental conditions. And we knew that there were a lot of central neurotransmitters involved, including quite widespread neurotransmitters like serotonin and dopamine. And there were some drugs around in those days, like fenfluramine, that worked on the serotonin system, that were used for appetite control, but they turned out to have significant problems with cardiovascular complications and were all withdrawn. So my PhD, and I'm going to try and summarize my PhD in sort of 1 or 2 slides now, because otherwise we'll be here all night. But I worked on different animal models of obesity, and one of the models I worked on was this little fellow here called the obob mouse. And you can see the obob mouse is pretty large. And the work that I did was to demonstrate that the obese mouse, compared to the lean counterparts, had much higher expressions of neuropeptide Y in the hypothalamus, which controls appetite, than the lean ones. It also had lower levels of neurotensin, and we still don't know the real significance of that. Almost immediately after I published this paper in endocrinology, about a few months later, this paper was published in Nature demonstrating that the obob mouse, the reason why it was living with obesity, was because it had a defect in a hormone not in the hypothalamus but from fat called leptin. And this was, an absolute revolution in understanding obesity, because all of a sudden we had an identifiable genetic cause of obesity. We knew, and it was a hormone. And it was a hormone from fat that signaled to the brain that told us when we were full. And if we didn't have any leptin, then these mice developed severe obesity. And in fact, we now know that there are very rare cases of humans with leptin deficiency who develop severe obesity and can be treated with recombinant human leptin. So that was an amazing observation. And the kind of link there, which was highlighted in this paper, was that the part of the mechanism was that leptin was working to suppress neuropeptide Y, which when we gave it to rats made them really hungry. So if you switch that off, it's one signal. This is a highly redundant system, though. There are lots and lots of components to this system. And one of the other components that we worked on was GLP-1. And I was working in Steve Bloom's lab when we published this paper in Nature, which was the first observation that GLP-1 suppresses food intake in rodents. It's a rodent study. And it activated the neurons in the right parts of the brain and so on. So that was kind of the scene that was where I was just before I moved to Liverpool. We knew that obesity and diabetes were linked, and I was working on various things that might have something to do with controlling appetite. I was managing to fit in a few other things. I did a charity bike ride, raising money for Diabetes UK. That was in the local paper in the Hammersmith. That photograph was taken outside the Hammersmith Hospital. I still like my cycling, but it was nice to do that. Just before I left, it was the Ealing Gazette, actually. You can see that, September 1994. And then in 1996, Gareth Williams, who'd also previously worked in Steve Bloom's lab, persuaded me that Liverpool was a much better place and that I really had to become a Liverpool supporter, which I duly did. And there was a lot of enthusiasm. It was a fantastic unit to work in. And I was able to continue some of that basic science research, doing the sort of studies that I'd done at the Hammersmith, but moving a little bit more into clinical research as well. And so now what I'd like to do is talk a little bit about sort of where we are now before I move in, and some of the more recent stuff that I've been involved in. So we're now moving into an era where we've moved from the finger prick test that took 2 minutes and so on for type 2 diabetes to an era where we've got flash glucose monitoring and so on. I'll talk a bit about that in a minute. But we also had some developments of some newer glucose-lowering drugs, and I did quite a lot of work on drugs like rosiglitazone and pioglitazone that were made available for people treating people with diabetes in the sort of mid to late 1990s. And we were involved in some of these clinical trials that looked at cardiovascular outcomes in people with type 2 diabetes treated with these glucose-lowering drugs. And although there tended to be a trend for benefit, and if you put the meta-analysis together, it suggests that there is a benefit for glucose-lowering on cardiovascular events. In fact, there was a real problem with particularly with the Accord study, which used rosiglitazone, because it actually showed, although the overall event rate was lower, there was actually a higher rate of myocardial infarction and heart failure in people treated with that drug. So we've now got the problem in type 2 diabetes where our treatments might be lowering the microvascular complications like eye disease and kidney disease and so on, but they're actually maybe even having an adverse effect on cardiovascular outcomes. And that was worrying, but it also created some opportunities, and I'll explain why in a minute. Firstly, because the regulatory authorities got really worried about this, and they said, right, anytime you test a new drug for diabetes from now on, you've got to do a big cardiovascular outcome trial to show that it's safe. That's what this slide is really saying. You don't need to understand the differences here, but that's really what they were saying. And these cardiovascular outcome trials had to be big trials. They had to involve thousands of people, because otherwise you didn't get enough events to be able to be absolutely confident that the drug was safe. And I was fortunate enough to be working alongside a number of companies that were developing new drugs. And I'm going to talk quite a bit about two classes of drugs here. The SGLT2 inhibitors, and also drugs that work on the appetite control system that I mentioned earlier, the GLP-1 related drugs. So I made this slide when I was talking about at the European Diabetes meeting last year. And again, the point that the discovery of insulin changed the lives of millions. And in fact, there was an earlier discovery that relates to glucose in the urine. That was made in 1835. And this is a compound that comes from the bark of the apple tree called fluorizin. What was noted at that time in the 1900s was that it caused excretion of glucose in the urine. And what we now know is that it inhibits two glucose transporters, the one in the gut, which is called SGLT1, which is responsible for absorption of glucose from the gut, and another one called SGLT2 that is responsible for capturing all the glucose that is filtered by the kidney and stopping it being excreted in the urine. And we know that people with diabetes overcome that threshold because the blood glucose is really high and then it all spills into the urine. But most of us, most of the time, don't have glucose in the urine because it's all being reabsorbed, mostly through SGLT2, a little bit through SGLT1. And this compound fluorizin became the prototype for the development of drugs that everybody was a bit skeptical about to start with, that were basically designed to make you pee glucose. And what we do expect to happen, so these drugs work on the kidney, they block just the SGLT2, so they don't affect the gut glucose absorption, and they directly take some of the extra sugar out of the blood, so they lower the HbA1c, they lower the blood glucose. They also, you're losing about, if you're taking one of these drugs, you're losing about 75 grams, about 3 ounces of sugar in the urine every day. So that's 200 calories less, so maybe they produce some weight loss. They're also reducing the sodium load in the body because they're working on a sodium glucose co-transporter, so you're excreting extra sodium as well. So they do another thing that might be quite good for people with diabetes, which is blood pressure reduction. And indeed, that's what we saw in all of the clinical trials that were done to show. And they were quite effective glucose-lowering agents, probably a little bit weaker than metformin, but nevertheless, they got an approval for glucose lowering. But the companies also had to do these big cardiovascular outcome trials. And we'd had negative trials for other classes of drugs. So everybody was going, well, it's going to show the same thing. It's not going to show anything. And then we started to see the results of these trials. And they were really quite remarkable. Because when we looked at major adverse cardiovascular events, they were consistently reduced by these medications. I was on the steering committee for one of these trials, which actually didn't show that significantly, but it was the largest trial, the DECLARE trial. But nevertheless, if you do the meta-analysis, it reduces cardiovascular events. What's also become clear is that these drugs also have a dramatic effect on two other things that are really important for people with diabetes. One is heart failure, and they reduce heart failure by about 30%. So the effects on heart attacks are quite small, but the effects on heart failure are really big. And these drugs have now been approved not just for treatment of diabetes, but also for treatment of heart failure. So any cardiologists in the audience will have to get familiar with these drugs as well. And the other thing that came from wasn't even a primary outcome of these trials, but has subsequently been shown in dedicated kidney outcome trials, is that they reduce the rate of progression of kidney disease in diabetes. And again, I haven't got time to discuss the mechanisms there, but it's really interesting the way they work. They're complementary to the effect of ACE inhibitors to preserve kidney function. And here's the result of one of those studies. This is the DAPA-CKD study, which looked at dapagliflozin, one of these drugs, in people with diabetes and people without diabetes with other forms of kidney disease. You can see that the risk reduction here is really quite dramatic. It's pretty much almost halving, nearly 40% reduction in the progression of kidney disease. And this has been consistently shown across the class. So this is one of the new developments that really is changing diabetes, and it's also changing some other aspects of medicine as well. And as I've said, I was involved in quite a lot of those trials. The other group of drugs goes back to the point that I was making earlier about GLP-1 and its effect on appetite. So GLP-1, we've known about it for about 30, 40 years now, is a gut peptide. And everybody thought, in fact, Steve Bloom was one of the first people to report this in the Lancet in the 1980s, was that it's an incretin hormone. So when you ingest glucose or carbohydrate, the main stimulus to insulin secretion isn't the glucose going up in the blood, it's a hormone from the gut that tells the pancreas to secrete insulin. And that's what GLP-1 is. It's one of the two main incretin hormones, the other one being GIP, which I will mention very briefly at the end. And as I've said, we also showed that it's also part of our satiety cascade. It tells us that we're full after meals. And to cut a long story short, a load of these drugs have been developed that are now used for the treatment of diabetes. Most of them are injections once a day, but now we're moving on to once-a-week injections. And one of the drugs that I've done quite a lot of work on is this drug semaglutide, which looks a bit like GLP-1, but it has a couple of switches of amino acids that mean it doesn't get broken down quickly by the degrading enzyme in the blood, and it's got a big lipid moiety stuck to it, which means it binds to albumin, gives it a very long half-life, and also importantly means it gets into the brain. And interestingly, these drugs are very powerful glucose-lowering agents. They do lower HbA1c by about 1.5–2%, which is much more than the oral agents. But like the SGLT2 inhibitors, the real surprise came when we started to do the cardiovascular outcome trials. And I'm just going to show one here, which was the SUSTAIN-6 trial that we ran at Aintree with semaglutide. And you can see here that it reduced major adverse cardiovascular events, non-fatal myocardial infarction, and non-fatal stroke. It didn't have a significant effect on cardiovascular death, although some of the other agents have done so. So that, again, is starting to transform treatment of diabetes. as I've said, my interest came from obesity, and I was working on, we did quite a lot of work with liraglutide, which was a once-daily drug, which is already approved for the treatment of obesity. But perhaps the most exciting trial I've been involved in was this one, which we published just last year in the New England Journal of Medicine, which is step one. This is the trial of semaglutide for obesity. And we've never had anything for obesity that even gets close to this. So in the control group, who got diet and exercise advice throughout the trial, they lost 2.5 kilos over the year of treatment, of 68 weeks of treatment. With semaglutide, 15% weight loss nearly. And that is really unprecedented. The best treatments we've had before that are giving about half that amount of weight loss. Bariatric surgery, which I'm not going to talk about today, might give 20 to 25% of weight loss. So we're starting to get close to what we would achieve with bariatric surgery. Not only does it do that, if you happen to have pre-diabetes, which about half the people in the trial did, that's the 45% there, and you see it's resolving that pre-diabetes, although you get some resolution of pre-diabetes back to normal glycemia with the weight loss in the placebo group. It's much greater, and very few people went on to develop diabetes. If you give it to people with diabetes at this higher dose, it's already approved for treatment of diabetes, you get a bit less weight loss, but you do get very significant reductions in HbA1c that are greater than we see at the lower doses that are approved for diabetes. And finally, this whole class of drugs, and this is a review article, very nice review article written by one of our research fellows, Emily Brown, published in The Lancet last year, showing that all of these drugs, most of these drugs have been consistently shown to reduce major adverse cardiovascular events in type 2 diabetes. And as I've already said, I think I've got another slide here on the SGLT2s. So we've now got two classes of drugs that are really quite effective for diabetes, and that's translated into the diabetes guidelines. So when we look at the latest American and European joint guidelines for diabetes treatment, if we're worried about weight, which is nearly everybody, if we're worried about the patient having kidney disease or heart failure or heart disease, then these are the preferred agents. And that's a complete transformation from where we were 10 years ago, or even 5 years ago. So it has changed a lot. Before I move into, I'm just conscious of time here, before I move into the last part of the talk, I just want to make one other point. Another piece of work that I've not been involved in, but we do have we have found some patients like this in Liverpool, is the fact that there is some diabetes that doesn't kind of fit into type 1 or type 2. And we're now getting quite good as diabetologists at making the correct genetic diagnosis and picking up these rare inherited forms of diabetes, because some of them can be really easily treated. So in fact, the best treatment for if you happen to have maturity onset diabetes in the young due to HNF1 alpha mutation, which is a transcription factor in the beta cell that affects insulin secretion, you can treat this and pretty much normalize the blood glucose with a small dose of sulfonylurea. So amazing change there. And that's just a small point that I wanted to make. So the last few slides, I want to just talk about some of the developments in technology in diabetes. So I've talked about drugs, technology. Most of this is relevant for type 1 diabetes, but it may become relevant in type 2 diabetes in the future. So we've evolved from the insulin pens, we've now got smart pens. The smart pens will record the dose you've taken, remind you to take your insulin dose at the right time. If you put your glucose levels in, they'll give you a calculation and tell you how much insulin you should take. So that is one way of where modern technology has really made a difference. The glucose monitoring technology has got a lot better. You need much smaller drops of blood. 2 minutes for the old BM sticks, it's now a few seconds, almost instantaneous. And these devices will link to your mobile phone and you can see what your glucose is doing. But perhaps the biggest advance most recently has been these advances in continuous glucose monitoring. So these systems basically are measuring interstitial glucose. They're measuring glucose in the interstitial space, in the subcutaneous tissue. And they're usually form of a patch with a little needle that goes on and stays in place for a week or two. And again, this technology is able to give you a pretty much continuous readout of your blood glucose. It can give you an alarm when your blood glucose is going low. It can give you an alarm when your blood glucose is going high, so that you can react accordingly. And in the last few years, we've had this flash glucose monitoring. You may have seen Theresa May had one when she was diagnosed with type 1 diabetes. And I can remotely look at what's happening to patients because they can upload their data to our systems. There's a system called LibreView. I can log in, and if a patient's got a problem, we can see what's going on. And when we can review their data, we can make much more fine adjustments. But the other great thing about this technology is that it really empowers the patients. And what we're seeing, we've been introducing this really only over the last 2 or 3 years in our diabetes clinics. And the patients, we see the control improving. It's so dramatic. It's probably more than we've ever seen. Because they empower the patients. They understand what's happening to their glucose. They understand when they eat certain types of food, their glucose goes up. Maybe they need a bit more insulin. Maybe they need to have a different type of meal. And it helps them adjust their exercise and so on. Really amazing differences that this technology is making. We've also seen insulin pumps getting much more sophisticated, and the kind of smart pumps are starting to develop, and some patients have these patch pumps, which are a bit maybe less intrusive than this type of thing. Nevertheless, of course, you've still got to have a reservoir of insulin. It's not a completely implantable device. The other thing, of course, that's been going on in the background to all this is things like pancreas and joint pancreas kidney transplants, which are being done. In the last 10 years in the UK, we've done probably about 1,800 pancreas kidney transplants. And the 5-year survival from having one of these, and often these patients are really have end-stage kidney disease, they're really quite ill with their diabetes. 5-year survival, nearly 90%. We've also, in this country, been one of the pioneering countries to develop islet cell transplants. They do them in Manchester, not here. But in the UK, in the last 10 years, we've done nearly 300 islet transplants. The main indication for these, which is injecting islets from a donor into the portal vein, where they implant in the liver and then continue to produce insulin, is patients with recurrent and severe hypoglycemia, which cannot be managed by adjustment of insulin doses. I don't think this is ever going to be a solution as it currently stands for everybody, but it can be absolutely life-changing for those individuals. Last few slides just on a bit of the future. We're moving closer and closer to the idea of the artificial pancreas. I showed you the biostator earlier. We now have systems that are available using glucose sensors that talk to the pump and that will actually tell the pump how to secrete insulin, how much insulin to give. The difficulty here is the algorithms and getting them to work. They work fine at night. They work pretty well if you're kind of pretty sedentary. If you start to exercise, if you have big meals, you have to there's still quite a lot of user input required. There are probably a few hundred people around the world who have hacked these systems and developed their own software that works for them. The real computer bots have done this, and some of them are able to control their diabetes amazingly well with almost no user input. But they've written their own software to having hacked the pump and the glucose sensing equipment and get them to talk to each other. The other advance is whether we can use stem cell technology to restore beta cell function in diabetes, or whether we can use immunotherapy to treat diabetes. Those things are still in their infancy, but nevertheless, those ideas have been around for a long time, and there's a number of companies working on them. And the other is whether you can make artificial islets or use islets in a way where they're protected from the immune system, but the insulin can still get out and the glucose can get in, and you could actually have basically a biological artificial pancreas. And there are companies such as this company in the US, Beta O2 Technologies, that claim to be developing this type of technology, but I've not seen anything actually working yet. And then finally, where are we going with the drugs? I've talked a little bit about GLP-1. There's another incretin called GIP that everybody thought wasn't important, but we've done a bit of work on this as well. And in fact, there is now a drug that works on, just literally approved by the regulatory authorities in this country a week or two ago, called tirzepatide, which is a dual agonist of GLP-1 and GIP. And this seems to be even better than the semaglutide that I mentioned earlier. So this is one of their many trials, and you can see they've compared it to semaglutide in diabetes, and you can see that it's better at lowering the HbA1c, and it also seems to produce better weight loss in people with diabetes than semaglutide. So that's one that's in development. And the other one, which we're actually just about to start a clinical trial of, is putting semaglutide with another gut hormone called amylin, where this phase 2 trial is showing 17% weight loss after just 20 weeks of treatment. So that the curve is still going down. So that's another exciting development for the future. So to summarize, we have come a long way in 100 years. We've got much better understanding of the biology. I haven't talked much about genetics, but we do understand a lot more about the genetics, which will lead us to that precision medicine for diabetes. I think for type 1 diabetes, most of the focus on the moment is around the technological solutions that I've talked about. And these are really making differences to the lives of people with diabetes, and they're getting better and better all the time. It's really fast. It's like the development of the phones and things that we've seen in the last 20 years. Diabetes is a little bit behind yet, but it's going very fast. The biological solutions, I think, are possible, but I think they're a little bit further away. But nevertheless, there's some quite exciting things to do there. And for type 2 diabetes, I do think that the key to this is weight loss, and we do now have tools that allow us to do that. And we do have agents that can prevent cardiovascular disease and kidney disease and progression of diabetes. So I think we are in a very, very different place, certainly to 100 years ago, but even to where we were 25 years ago when I first came to Liverpool. Thank you. And I'm happy to take questions. Yes.
So, John, fantastic lecture, really enjoyed that. Do you think with type 2 diabetes, we're coming close to the situation where rather than waiting for disease and complications to have developed and have been established, that we'll be looking at perhaps in 5-10 years of, as I've just done, start on a statin, we'll turn around and say, actually, it's time to start doing a tide.
Yeah, I think we probably are getting quite close to that point. I think it's going to take a little time because these drugs are still pretty new. Although we've had GLP-1 analogues, I mean, the first one, exenatide, was launched in 2008. But it's taken a long time for the data to emerge, and the new ones are much, much better than the old ones, and they're much easier to use. You know, we'll talk about weekly injections. There's possibilities of implants and things that would, it'll be like, once every 6 months. Potentially, so I think you're right, but the difficulty there is it's technology, it's cost. I mean, semaglutide, it's interesting that they launched their obesity drug in the United States last year, and they very rapidly run out. At the moment, we've got a shortage of both semaglutide and one of the other ones, dulaglutide, in this country, in fact globally, because there's been such a demand for these agents, and Novo Nordisk are building a brand new factory in Denmark, which means that that problem will be solved early next year. But at the moment, that is an issue. So these are biological. They're peptides. They're quite complex things to make. It's not a small molecule that chemists can knock up in a lab. These are biological molecules that are difficult to produce and require very, very, and then they're expensive, and that's the other issue.
John, how come athletes don't get fat? I mean, they eat an enormous amount of food.
Yeah.
Does exercise control their need for food, or how do they feel full and don't eat anymore?
Well, if you're exercising a lot, then you need a lot of food. So, I don't want to boast, but I did an Ironman a few years ago, and I think my daily calorie need, estimated by my smartwatch, was something like 6,500 calories that day. So, I was probably eating twice as much for a day or two afterwards just to catch up, because you can't do all that in a day. And likewise, if you take people who do a lot of exercise, the greatest example I can recall is when Ranulph Fiennes walked across the Antarctic. I think there was a talk here about that a few years ago. That they're burning, because it's cold and they're walking all day, they're burning 7,000 or 8,000 calories a day. That's almost more than you can actually eat. So in that situation, you're actually burning more than you can eat, and so you're losing weight even though you're eating 7,000 calories a day. And you're still actually feeling really, really hungry, even though you're eating 7,000 calories a day. So it's not about how much you eat, it's about, the body is sensing energy requirements in ways that, leptin is part of it, but it's probably a lot more complicated than that. And we don't fully understand all of that yet. That's kind of a partial answer to your question. But we debate this a lot in the obesity.
Dieting alone isn't enough. You have to exercise if you want.
Exercise is good for you for lots of reasons. It's not a very good way of losing weight, because you have to do an awful lot of exercise to lose weight. But it's very good for you.
I think it is right that if you're a super athlete, you reduce your insulin requirements. You're a rower.
Oh yeah. So Steve Redgrave developed diabetes just before he got his final Olympic gold medal, and he was at that time, he was a big lad. He was probably using and doing a lot of exercise, and big muscle mass, which is your lean body mass is probably the most important thing in terms of energy requirements. He was requiring a lot of energy. And there is some discussion about whether, I actually know the guy who looked after him for his diabetes, but there's some discussion as to whether actually giving a little bit of extra insulin actually helped him, because it's anabolic, and if you take a lot of protein with insulin, where's that protein going to go? It's going to take up into your muscle. And so it is a trick that athletes sometimes use, is to have lots of carbohydrate, lots of protein, get a big insulin boost, natural insulin boost, and that will actually help them build muscle.
John, great talk, thank you very much. Diabetes is very expensive for this country. I think something like 10% of the cost of the health service falls in diabetic care. Do you think these new developments are likely to lead to a reduction in the burden on the health service?
Yeah, that's a great question. I mean, obviously NICE spends a lot of time looking at these things, and everything that I've talked about today is approved by NICE on the basis of it being cost effective. Now, that doesn't mean to say that it's doesn't cost money, but it's considered at least cost effective. I think the answer as to whether it's going to eventually save money, I think we're going to have to probably look at a longer time frame. I think these technologies for type 1 diabetes will almost certainly save money in the long run. And some of these other treatments that reduce cardiovascular disease, for example, the SGLT2 inhibitors, we did some economic analysis based on the Claire trial, and actually in a lot of scenarios in the sicker patients, it actually works out as cost saving, which is very unusual for an economic analysis. So the answer is maybe.
Presumably, if one can reduce the side effects of cardiovascular and renal disease, that will keep people at work longer, and we reduce the costs of dealing with those parts of it, even if the cost of the treatment for diabetes is high.
Absolutely, and of course those costs are never considered in health economic analysis that only look at health outcomes. But if you think about obesity, the number of people who are not working or retiring early because of problems related to weight, if we have effective treatments there, I think that could make a huge difference in the long term. And certainly we see examples of that in our weight management clinic with people who have bariatric surgery who've not worked for years, and then they're back at work because they're now able to function in society again.
The factor that seems to have disappeared from healthcare is prevention. And given that 1 in 5 children are now overweight, aren't we just making type 2 diabetes for the future?
Yeah, I mean that really scares me. And of course, everything I've said here should be on the background of making the right decisions in public health. And it's really depressing that we currently are in a situation where those public health budgets are being cut when they should be increased, and we also need to be thinking about how we support, particularly in deprived communities, we support parents to feed their children healthier meals and so on, and try and move away from the addiction to junk food that is driven by the big food, if you like, and that's the problem. You have that lobby of big food, and governments are a bit scared of that.
Yeah, when you think of the number of aisles in the supermarket that's devoted to junk.
Yeah, and there are countries that have made those changes. Mexico, in fact, is really leading on that at the moment, and so is Chile. And countries like Finland did it a long time ago, and they have much lower rates of obesity and diabetes than we do. Yeah, David.
Really good talk, enjoyed it. You talked about prevention of type 2, what about prevention of type 1?
Yeah. So prevention of type 1, I think at the moment, we don't know enough about the etiology. I mean, people have done, we know a lot about the immunology of type 1 diabetes, but we've never been able to find an immunotherapy there are a few immunotherapies that have shown a little bit of promise in phase 2 trials, and then when they've got into larger trials, they've been unsuccessful. And in terms of, there's two factors there. One is we've got absolutely no idea what the environmental trigger is. It might be food, it might be a virus. I mean, there are lots of ideas, but I don't think there's anything that we absolutely can pin something definite on. And then, of course, you've got the problem that, okay, if you've got a family member with diabetes, you've got a higher risk, but how do you identify the people who are developing it? Because we know that the pathological process that leads to type 1 diabetes might go on for many years. So you'd actually have to probably be serial. Do you serially test all children for islet antibodies and so on? I mean, and then give them potentially toxic immunotherapies in the hope that they might not get diabetes, because that's the level where we're at the moment. It's really difficult.
As a parallel to that, my understanding as a non-endocrinologist, if you have a family member with type 2 diabetes, you have a higher risk than the general population.
Absolutely.
So, is there any simple measure in terms of BMI, size of your waist, whatever?
Yeah, so there are some really good tools, and in fact there is actually a national diabetes prevention program that is already being run. So you can actually go to the NHS website. Basically, the factors that are used for the diabetes risk prediction tool are your age, your gender, your BMI, your waist circumference, and your blood pressure and family history. If you know those things, it gives you a pretty good prediction. And in fact, if you add everything you know about genetics to that, it improves the positive predictive value from 79% to 80%. So, you don't really need to do anything very sophisticated. You can put your stuff in that, and then there is it's a 16-week sort of lifestyle support program, but it has been shown there is data out there that shows that it works. I didn't include all that because I wanted to talk about treatment rather than prevention, but I do think prevention is very important.
Is there a benefit for people with type 1 diabetes with some of these newer drugs?
That's an interesting question.
Teenagers who deliberately reduce
insulin. So the SGLT2 inhibitors, one of them was for a while approved for type 1 diabetes, but there was one of the problems with that is keto. With the SGLT2 inhibitors is because of the way they work, you get an increase in ketones, and it can tip people in type 1 diabetes into ketoacidosis very easily. And although you can manage that, and there were some people who were doing really well on these agents, in the end, the company made a voluntary decision to withdraw it from the market because I think they were just running a bit scared of what might happen. The GLP-1s, there have been some trials of some of the earlier ones in type 1 diabetes, and they didn't really show much benefit, but again, the question is being asked again with the newer agents that are longer acting, and maybe we talk about some people having double diabetes because they've got all the phenotype of type 2 diabetes, but they've already got type 1 diabetes. So, maybe for those individuals, some weight loss and getting rid of the fatty liver and so on would be beneficial. But I think we still need to do those trials.
And then I just wanted to ask about gestational diabetes in terms of anything new. Obviously,
some of this can apply here?
Yeah, I mean, I think gestational diabetes, the way that's being managed now is with a lot more of this new technology to support people. So, you know, Libras and so on are given to everybody with gestational diabetes. So that kind of, and with type 1 diabetes, you can have the more sophisticated continuous glucose monitors. So the management is a lot better. For type 1 diabetes in pregnancy, it's like that. With gestational diabetes, it's still basically metformin and insulin, because we don't really know much about the safety of these other drugs in pregnancy.
May I ask, has NICE approved pancreatic transplants and islet cell transplants, and have those recipients of either been subject to the scrutiny of the drugs that have been used for diabetes?
Yeah, there are big international registries for these transplantations, and this is, it's all, the islet transplants are funded by NHS Specialist Commissioners, so it is commissioned by the NHS. I think NICE has said that, you know, it's an option for those individuals, but it is very expensive. It's a very small number of, you know, many tens of thousands of people with type 1 diabetes who will be offered those treatments. The pancreas and kidney transplant, for often, is really the only option for these people who have got end-stage kidney disease and difficult to control diabetes, and it is very effective. Okay, that probably brings proceedings to a close. So thank you very much, everybody, for listening. I hope you enjoyed that. And we've got a next meeting, I think it's the 15th of December, and Tom Solomon is going to talk to us about Roald Dahl. Does anybody know Tom Solomon? Tom Solomon is a neurologist, and he actually looked after Roald Dahl during his last, Roald Dahl, the author. So he's going to tell us all about Roald Dahl and a few other interesting people he's met on the way.
Thank you.